I'm going to tell you more than about the Wisc. And the reason I will tell you more than about the Wisc is that there wasn't enough in the Wisc to take up the hour. But I will start out by giving you a little story about how I got into the computing field. When I went to the University of Wisconsin, I went there as a theoretical physics major. In fact, most interested in the structure of the nucleus. And in the fall of 1949, I was given an assignment along with two other graduate students to determine whether or not a proposed force between nuclear particles could describe the simplest three-body nucleus. For 30 days, the three of us used a desk calculator with 10 digits and a slide rule to hold two more. And we mapped the energy state of the simplest three-body system, tritium, for all values of the parameters, and ascertained that the lowest energy level was still not quite bound. And I decided there had to be a better way. So I began to invent something to do this computing. The first thing I did was come up with a design for a machine I called an electronic digital differential analyzer. We never built that one, but it turned out that independent of my activities in that area, such a device called MADIDA had actually been designed essentially concurrently in California. That following summer, I went to the Aberdeen Proving Ground and got a chance to see the ENIAC and a machine that was under construction called the EDVAC. And I went back to the university at the end of the summer with an idea for how one could make something very simple, or so I thought. And that machine was the machine that ultimately got called the Wisc, which stands for Wisconsin Integrally Synchronized Computer. The Wisc was a machine that had a very simple instruction set, just 10 instructions. It was a 3-address instruction set, and it operated in floating point. As a matter of fact, it operated only in floating point. It had, other than a branch and a stop instruction, it only had one other instruction that wasn't floating point. And that was an instruction that allowed one to move a string of bits of arbitrary length, starting at an arbitrary place in one word and to a second arbitrary place in the result word. And so one could take the components of the floating point operands, such as the exponent or the fraction, or an address in an instruction, and move it to a place where you could do arithmetic on it without the having any kind of normalization take place in the floating point operations, so that you could do the floating point arithmetic for address modification, for example. And that worked very successfully. Actually, we had one redundant instruction. The branch instruction was really the redundant one, because I had a compare instruction in it. Basically, we had add, subtract, multiply, divide, compare, extract, branch, halt, input and output. Those were the 10 instructions. And the coding was extremely simple, extremely straightforward. The compare instruction, for instance, would compare one operand with a second and branch to the third address. And so one could have always set it up to compare a 0 against a 0 or anything against anything and end up with a branch. And so the branch was unnecessary. However, the proposal I made for that machine to the university was sufficiently interesting so that the university decided they wanted to do it. And so they got my major professor to change my thesis subject to making a record of the plan for the machine so that they could build it in the engineering department, not as a computing tool, but as an educational tool for training their electrical engineers in this new field called computers. This was fall of 1950. And in January 1951, I began my first work in the electrical engineering department, both starting the project and writing my thesis on the design of that machine. It was completed by June of that year, and I received my PhD on that the following February.
Well, this morning, communities in the state are still assessing the damage from Friday's tornado.
But as recovery efforts continue, Governor Andy Beshear is warning about a weather radio outage as a new round of storms head our way. The governor posting a message on Facebook last night saying there is a heightened risk for dangerous winds, hail, and tornadoes. The governor also saying there is a NOAA weather radio outage due to updates through Wednesday. The governor says you should find an alternative alert system if you rely on a weather radio for warnings.
Somehow, the National Weather Service and NOAA chose to do a systems upgrade that is currently going on and won't be finished until Wednesday. That means your weather radio won't work if you have one.
Governor Beshear says even without weather radios, you should keep your phones charged and your weather alerts on with a plan to shelter if necessary.
I'm Dr. Marshall Shepard, and I'm the Director of the Atmospheric Sciences Program at the University of Georgia and the Georgia Athletic Association Distinguished Professor of Atmospheric Sciences and Geography.
My name is John Trostel. I'm the Director of the Severe Storms Research Center here at GTRI.
We're rivals on the football field in sports, but we are locked at the hip when it comes to studying weather and improving access to information, data, and understanding for our state. And so I was ecstatic when my colleague John Trostel reached out to me with this opportunity, because it represented another way that the University of Georgia and Georgia Tech can collaborate. I've been involved in recent collaborations on things like Drawdown Georgia or the Georgia Climate Project, which focus more in the climate space. This is a real opportunity for us to collaborate to understand better weather in this state, teach our students, and perhaps even provide a service for citizens and those living in the state of Georgia.
I actually was online one night and saw a used weather radar going up for sale from a company that's very well known in the weather radar community. They were going to put up their latest radar, and so their research radar was being offered. I got in touch with a collaborator at UGA, and we put together a consortium of folks from UGA and Georgia Tech and GTRI to put up the funds for this computer. So UGA has put in half the funds, Georgia Tech has put in the half the funds. It's been quite an interesting collaboration.
It's a game changer from several perspectives. One, we know that there are gaps in parts of northeast Georgia, or the places where the radar from the National Weather Service is too high. Even the terminal Doppler radar at the Atlanta airport, there's a large landfill that blocks some of the radar beam.
And that radar is designed specifically to aid flights coming in and out of Hartsfield Airport to look for signs of wind shear and severe storms in the area of the airport. And the problem with the TDWR, as it's called, is there is a landfill that's situated just to its northeast. So there's a big pie-shaped area in the reflections coming back from the TDWR that are blanked out. Our radar will actually be sitting in that area when we have it in its final spot, so it'll fill in that whole gap. And so the National Weather Service and the folks at Hartsfield Airport will be able to look at the returns from our radar to see if there's anything of concern in that area.
Well, we can never have enough weather radar coverage, particularly with the storms and rainfall that we experience in Georgia. Now, the National Weather Service and even some television stations have longer wavelength radars, and they can give you extended range coverage, which we need. This radar is unique because it's an X-band system, has a shorter wavelength, which means it has less range, but the importance of that is that it can fill gaps. We can get detailed looks at places perhaps that we're missing with some of those radars, or that we want more detailed information about for our research or teaching at Georgia Tech or the University of Georgia.